入语中。Okay, while all they are writing, let me explain it a little bit. So please write it down, and please start. After you write down these two problems, you can start calculate the first one. Okay. So let me explain it a little bit. So in this problem, it asks you to use Kirchhoff current law to find IA, IC, and ID. And so in this case, several currents are known. So we know the current flow through the element B, no matter. So this block means it doesn't matter which element B is. So it could be a battery, it could be a resistor, it could be capacitor, inductor. Questions? OK, F 它本来就没有，但这个跟我们解题没有关系，我们解题不需要 F。OK， 好，这个没有加到，因为这不是这个题目本来就没给。OK, and so in this problem, we see that some current is given. The current flowing through B, its value and direction is given. Okay, and the current flowing through here, through this wire, is given, is 3 amp. And then the current flowing through element E is given. And its direction, both its value and direction are given. Okay? And there are several things that are also given. IA, even though it's a variable, but its direction is given. It's assigned by the problem. Because, as I mentioned, we don't know the value and the direction of a current unless we solve this circuit. So in the beginning, it may be right because its direction may be right or may be wrong. Okay? And if you calculate IA is a negative value, then it means its current flowing through A is from bottom to top. Okay? And also the same thing, we assign the problem gives you IC, the direction of IC, and also the direction of ID. Okay. Okay, everyone, you can stop writing right now. And then, so please focus on this problem. So in this problem, we can observe a few nodes. The definition of a node is it connects two electric elements. So how many nodes here? Let me call up. Okay. So nodes is one node. Two nodes, three nodes, and yes, there are only three. Why? Okay, this node connects at least two elements, and this node, you can think this is a big node because they are connected together. Okay, so the second node. The third node here. This node connects to 1, 2, 3, 4 elements. So you can identify three nodes here. And you can apply KCL, Kirchhoff current law, to this node. So let's say this is node 1. This is node 2. Yeah, this is node 2. This is node 3. Okay? So if we look at node 1, yeah, how about I just write down the equation for you. But you have to calculate on your own. So KCL tells us two things. So if you have your notes, because we talked about KCL last time, So KCL tells us two things. The net current entering a node equals the the summation of the current entering a node is 0. So this is the definition of KCL. The summation of the current flowing into a node is 0. So if we use this definition, and then if this current is flowing out from node 1, we need to say this is minus A. Okay, so if we follow this definition, for node 1, we can get one equation. So it's minus IA plus the summation of current entering a node is 0. So enter is positive, leaving is negative. So also leaving minus 2A minus 2 equals 0. Okay, so they are both leaving this node, so it's minus A plus minus 2. Okay, so let me make it more correctly. Minus A plus minus 2 equals 0. And so we can know IA. So IA is minus 2n. Okay? And so we know because IA is now a negative value, it means it's flowing upward. So for node 1 is the simplest form. So the current entering to node 1 is 2n, and the current leaving node 1 is 2n. There's no other branch. OK， 好，那我用中文稍微很快的说一遍哦。我们用这个赫西霍夫的电流定律，它告诉我们，流入一个节点的总电流和为0。OK， 那因为它是流出，所以我们就是加一个负号。它是流出，也是加一个负号。所以呢，虽然说我们定义是流入，但是因为它是流出，那我们就是负 IA 加负2，因为它们都是流出，我们放个负号等于0。那我们就可以把 IA 解出来是负2安培。那如果是负2安培，但是 IA 它的定义往下，代表说 IA 实际上是往上2安培。OK， 但是为了不要搞混哦，因为题目给你 IA 往下，所以我们答案呢就直接写 IA 等于负2安培。那 so it's a minus, but the problem give you the definition of IA is going down. So our answer keep this. We do not change we do not change our problem. So this is the right answer. Okay? And it goes another definition is so this is one definition of KCL. Another explanation could be the current flowing into node 1 equals the current flowing out from node 1. So since IA is minus 2A, it's 2M flowing into node 1, it's equals to IB, the current flowing out from the same node. Okay, this is the first equation we can receive from node 1. And then we look at node 2. Okay, if we look at node 2, so node 2, we look at the summation of current flowing into node 2 equals 0. Okay, so IA flowing into node 2, so it's IA, IC leaving node 2 minus IC, ID flowing into node 2, so it's plus ID, IE leaving node 2, so it's minus 1 equals 0. Okay? And then we know IA, so we could put IA here. We could put minus 2n, minus 2. We can replace IA with minus 2. But there are two unknown variables, just one equation. That means we need one more equation. So luckily, we still have node 3. So node 3, same thing, the summation of current flowing into a node equals 0. So from node 3, well, actually, okay, I write the correct way. So let me write the correct way. So the correct way is 2, because IB flowing into node 3 plus IC minus IB plus 1 equals 0. Okay? So you have 3 nodes, 3 variables. Huh? Yes, that's what I say. Let me show you the correct way. Okay? And so I will talk about this later because it gives us one more condition and make it easier to solve. But even without 3A, we can still solve it. Okay? So this is the correct way to list all 3 equations with 3 unknown variables. Alright? And before you solve it, actually this problem gives us one more condition. It's 3 amp current flowing to the right. So, although this is a no, because they are all connected together, but because it gives this condition, so we can focus on this. How about, let's say, node 4, but this is extra. Okay, so even without this, you can still solve it, but since it gives you 3 amp here, so if you look at node 4, so let's say node 4, current flowing into the summation of current flowing into node 4 equals 0. So 2 plus IC, they are all flowing into node 4 minus 3A is 0. Okay? It's equivalent to 2 plus IC equals 3. Okay, so it's the same thing. So if you are written as 2 plus IC equals 3, it means the summation of the current flowing into node 4 equals the current flowing out from node 4. So we can solve it easily. IC equals 1. Okay, IC equals 1. So this is another answer. This is one answer. So since IA is minus 1 and IC is minus 2 and IC is 1, so we have, so this becomes minus 2 minus 1 plus ID equals 1. So ID equals 4 amp. And we can double check. So we put ID and IC here. So yes, it's correct. Okay, so that's why I say it gives an extra condition. Okay, but even without this, we can still solve it because you have 3 nodes and 3 variables. So this is how we use KCL. Okay, any questions? Do I need to explain in Chinese? Okay, very good. Yeah, because I will, this time, okay, for this I really need someone I will call someone to solve. So let me explain this problem first. I can show you, first of all, can anyone tell me how many loops within this circle? No. How many loops? No, it's not 2. Anyone? Yes, 6. You got it? Okay. Tell me your name later when we have 2 bonus. Yes, 6. 1, 2, 3, as long as it forms a closed loop, is a loop. 4, 5, and the outside loop 6. Okay, so it means each loop we can generate an equation. So which means it can generate 6 equations. So if we look at a node, so we can identify 3 nodes, so we can write 3 equations. And 3 equations can solve 3 unknown variables. 6 equations, it can solve up to 6. But actually, we just have 2 variables. So any of 2 of 6 can use to solve these 2 variables. I solved one for you, but I want you to tell me the second. So to apply this Kirchhoff voltage law, if you look at the definition, it tells us the summation of the voltage within a loop is 0. Okay, that's if I'm right. Yeah, the sum of the voltage equals 0 for any loop in an electrical circuit. We look at this loop, okay? And then my personal habit is I will start from the bottom left here. So because I'm going to calculate the summation of the voltage within this loop. So the way to do it is I start from here. When I meet a negative sign, it's a negative, so it's -3. So I say it's loop 1. So loop 1, -3, -5, plus VC, because when I hit here, plus VC equals 0, so VC equals 8 volts. Okay, well, it seems, okay, I solved this for you, but really, next time I will call someone to solve it for us, because yeah, it's you are the one who's learning, right? Not me, I already know. But here there are a little trick. So any questions? The little trick is here. You notice I use a red because I use -10 volts. If it is given minus plus and give you -10, it means you have to change this a little bit. So it means here, so minus is positive, so it should be positive 10 volt here. It should be here. It should be positive on the left, minus on the right, because it gives a minus. Okay? And same thing. We apply KVL for loop 2. So same thing, start from the bottom left, minus VC, plus 10V, plus 10 minus VE is 0. So VC is 8, so VE is 2. Okay, one thing to talk about is you can double check, actually. You can double check with, wait, VC is -2, right?
不对，啊，那个不是负一，是正一，是加一。
Oh, okay. Yes. So this is -2V. So who's the first one to tell me? 谁是第一个跟我讲？啊，太多人了，那就下次再 bonus 吧。好，记得下次抢先讲。Okay. Yeah, I made a mistake. This is plus VE. So V is -2V. And you can double check with other loop. How about let's double check with this loop? So this loop, we double check with this loop. We double check to see if the voltage within this loop satisfies KVL. Okay, so minus, this is, we call it loop 3. So loop 3, it has minus 3, minus 5, plus 10, so plus 10, plus VE equals 0. So here, so VE is minus 2V. Yes, it also satisfies loop 3. So any loop, we have 6 loops. For any of them, they will satisfy KVL. Because KVL, KCL, and Ohm's law. And Ohm's law, they all need to be satisfied. Okay, when you analyze the circuit. Okay, so any problems? So any questions or problems? So we go back and take a look on the example that we talked about yesterday. Okay, no problems. Let me lower down the screen. Okay, does anyone need more time? Okay, no, very good. Okay, let's look at this one. Yesterday I asked you to put V1 to assign this variable as V1, right? And also this is V1. So we don't want you to confuse this variable with voltage. So V1 actually is, okay, so this is V1. Yesterday this is V1, and V1 is 3.333 volts. V1, we have I2. Yes. Huh? I want to talk about KVL. Yeah, because yesterday we used Ohm's law to solve everything, and then I'm thinking about, yes, we can use KVL because I want to prove that KVL and KCL, they also satisfy this circuit. So V1 is 3.33 volts. So how about, let's see. So we are able to calculate the remaining voltage and current within this circuit. And So yeah, that's the. We will move on after we finish this. So let's look at here. So this is 20 ohm. This is 5 volts, and then this is 20 ohm. This is 40 ohm, and we already know where the V1. V1 is 3.333 volts. Okay, and again, when we make the analysis, we always assign a reference node. At this reference node, the voltage is 0, and we usually assign the bottom node as our reference node. So here, for these all 3 points, its voltage is 0. And then, since there's a 5 volt voltage source connected to the reference, so we know here is 5 volt. This node and this node, they are 5 volt. And then, so this is the first step. The first step is you need to identify reference node. And then the second step is the current flowing through a resistor always flows from high potential energy to low potential energy. So we know the current here should be I is 5 minus 0 divided by 20. 0.25 amp. Okay, and then we know from Ohm's law, we know V equals IR, right? If there's a current passing through the resistor, and then multiplied by its current multiplied by resistance, they are 0.25 times 20. They are 5 volts. So we are able to mark this positive minus 5 volts for this resistor. So within this loop, you have minus 5 plus 5 equals 0. KVL also this KVL also holds. Okay. So and then how about if I ask you? So this is I is 0.25, and then how about if I ask you the current flowing out from the voltage source? How to calculate this? Let's say this is I1. This is I. Oh, we already have I2, right? We have I. So this is I. This is I1. Okay. This is I1. Okay. All right. I1. How about if I want you to calculate I? Okay. Actually, if you have V1, so the current passing through this, we say is I2, right? I2 will be 40, will be V1 divided by 40. Okay, this divided by 40. Okay, and then you can apply KCL at this node. The current flowing into this node will be equal to the current flowing out from this node. So I equals I1 plus I2. So, and then I'm not going to calculate this. Please calculate it on your own and compare your result. So yes, by KVL, KCL, and Ohm's law, we can solve all the currents and all the voltage inside a circuit. Okay, so yeah, that's how. So here, look at the source, look at the voltage source, and yes, there's a current flowing from the voltage source, but we don't know. It usually flows from positive terminal because it provides energy, right? If you remember yesterday we mentioned, as long as the current flows from the positive terminal of an element, it provides energy. So current, we know I flowing out from this plus terminal, but we don't know its value. That's the way to calculate its value. Okay. And same thing here. We don't know the voltage. We don't know the voltage across this dependent current source. But that doesn't mean it does not have a voltage difference. Yes, it has. As long as we calculate the current, it flows to 50 ohm. It's positive minus VA. So here should be, so yes, same thing. We apply KVL, positive, negative, and then so minus plus equals 0, and then we can calculate the voltage across this dependent current source. Okay, so we can solve every voltage and current inside the circuit by using just 3: KVL, KCL, and Ohm's law. And you should always consider Ohm's law first. You try to observe the structure of the circuit and make the easiest calculation. So that's why yesterday I only used Ohm's law, and I can solve this VA because it doesn't ask you I. You don't need to apply KCL and KVL. Okay, just try to observe the question and try to think how can you solve this variable easily and quickly. Okay. All right. So any questions? So remember, start doing your homework because we will have a quiz next week. From the homework, I will pick maybe any problem from the homework. So you have questions, you need to ask me. Okay. So we can move on. Any questions? If you have no more questions, let's talk about resistive circuit. The so-called, okay, do you need more time to write it down? Okay, does anyone need more time? You can stop for a while. If you need more time, please raise your hand. No. Okay. The major difference between Taiwanese students and probably the students from America or South America is they talk a lot. Okay, and then they are not afraid to talk. They will express themselves more, and actually, you remember that my students go to ASML. When they recruit people, they are trying to find someone who is talkative because you need to communicate within a team because their project's too large and it cannot be done alone. You must work with people. So to work with people, you need to talk to people. So yeah, so we can practice in our class. Okay, we look at this chapter 3. So resistive circuit means within this circuit, it only consists of resistors and sources. These sources may be current source or voltage source. Okay, but it's the element which consumes energy only. They are only resistors. So resistors and source. So if we can combine several resistors and replace by an equivalent resistor. And you must learn this before. So for example, for resistors in series, R1, R2, R3, they are in series, and then we know the equivalent resistance is the summation of R1, R2, and R3. Okay, and actually it can be proved. It can be proved by KVL. So suppose we are given a voltage source to these two terminals, and this voltage source, it has positive on the top, negative on the bottom. So let's imagine this forms a closed loop, because the current will only flow within a closed loop. So minus V plus V1 plus V2 plus V3 equals 0. So we have, and then we also have V1 equals R1I. Suppose there's a current I flowing into these resistors, and they are consuming energy. So automatically you can assign a positive sign here. It's because the current always flows into the positive terminal of a resistor. Okay, and then you put here and use KVL, replace V1 with R1I, V2 with R2I, V3 with R3I. And then, so you can have this. You can sum up the R1, R2, and R3 and make them become an equivalent resistance Req. Okay, so if you look at here, it's just simple Ohm's law. So that's why we say when these resistors, they are in series, we are able to use an equivalent resistor to replace them. Okay, and then for series condition, it's just very simple. You just add up their resistance. Okay, so we don't need to talk more about it. Okay, and for resistors in parallel, we have R1, R2, R3 in parallel, and then we assume that we give it a voltage, and the currents flowing from top to down. And we have I1, I2, I3. And by using Ohm's, okay, because they are in parallel, one thing to notice, since they are in parallel, okay, so this here, actually they belong to the same node because they are all connected together, right? And here, they are all connected to the same node. And then we apply a voltage difference between these two terminals. It means for the voltage across R1, voltage across R2, and voltage across R3, they are all V. They are all V because they are in parallel, they share the same nodes. They share the same top node and bottom node, so they share the same voltage difference. Okay, so I1, so each of them need to satisfy Ohm's law. So you have this, and then you can apply KCL on the top node. I equals I1 plus I2 plus I3, and then you replace I1, I2, I3 with V and R1, R2, R3. You can receive this. And then it is equivalent to a simple Ohm's law. So you have this formula, 1 over R equivalent Req equals this. Okay, that's where this formula comes from. You have, as long as R1, R2, and R3 in series, in parallel, you have this. You can calculate its equivalent resistance. Okay, so you must learn this formula before, but you may not know where it comes from. Okay, but so if R1, R2, they are equivalent, and if they are all equivalent, if they are n number n of resistors, they are in parallel and they are equivalent, and they are in parallel, its equivalent resistance is just R over N. Yeah, you can easily prove this by assign R1 equals R2 equals R3 and equals Rn. And then equals R. Okay, so is a 1, and then if there are just two resistors, the equivalent resistance is just R1 times R2 divided by R1 plus R2. You can memorize this because it will make you easier. It will be easier for you to remember and to calculate. Okay, so, but they are the same thing, just this formula. Okay, so any questions? Okay, so yeah, you have to calculate this. Find the equivalent resistance. If we look at here, if we look from this direction, so which means find the equivalent resistance between these two terminals. And I will give you some time to calculate. I will ask someone to show us when we come back. So we can start the calculation and then take a break at 11:10. Alright. 好，可以帮忙关一下那个摄影机，按一下。